Most people hate statistics and they would rather have nothing to do with it. But wishes are not horses. Many healthcare practitioners need to know statistics either for research or to understand scientific publications. I am Oluwadiya Kehinde. Over the course of 3 lectures, I will be taking you on a journey through statistics. This is the first of 3 videos I will be making on effective use of advanced statistical methods in medical research. I wish to thank the management of the National Postgraduate Medical College of Nigeria for inviting me for the program. In this lecture, we will be focusing on the first 3 objectives as we see on the slide. And those 3 objectives are why you should know statistics, what you need to effectively use statistics, and transformation of data. These are the issues that we will be focusing on in the lecture. At the end of the 3 lectures, you should be familiar with and be able to determine the usage of the most common statistic procedures used in research. Without wasting time, let's begin by digging into the first objective of the lecture. Statistics can be misused intentionally or unintentionally. The truth is, as Benjamin Disraeli inferred in his famous quote, statistics can be made to lie. A lot of published peer-reviewed articles contain errors. If we don't understand statistics, we will likely not see the errors. This may affect our practice. It will certainly affect the quality of our research. Over the years, many articles have been written on errors in scientific literature. In the next few slides, we will be looking at some of the articles. One of the most downloaded articles in medical literature deals with this problem. The paper was written by John P. Hay. Since I always have trouble pronouncing his name, I have learned to live well alone by abbreviating it to the Hay. And what's the title of this article? Why most published research findings are false. Why most published research findings are false? The most important findings on that paper were simulations show that for most study designs and settings, it is more likely for a research claim to be false than true. Moreover, for many current scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias. You see, lightning can sometimes strike twice. John produced another outstanding paper highlighting statistical errors in highly cited papers, and the title was Contradicted and Initially Stronger Effects in Highly Cited Clinical Research. What was the methodology he used? He selected original articles from the medical journals with the highest impact factors. Journals like the New England Journal of Medicine, JAMA, and the Lancet. Not only that, but he also only selected articles with at least 1,000 citations from these journals. He then compared the results from these aristocrats of medical literature with more recent studies of similar pedigree. What did he find? His findings did not look good for medical literature. 4 out of every non-randomized studies were wrong. Randomized studies perform better, but I am still disappointed that up to 25% of them were later found to be false. Every researcher should read that paper. It is an eye-opener. D.G. Holtzman was a world-renowned statistician. Listen to what he has to say about medical research. In an article, The Scandal of Poor Medical Research, D.G. Holtzman wrote, "We need less research, better research, and research done for the right reasons." He added, "We need not be experts in statistics, but we should understand the principles of sound methods of research. If we can also analyze our data, so much the better. Amazingly, it is widely considered acceptable for medical researchers to be ignorant of statistics. Many are not ashamed, and some even seem proud to admit that they don't know anything about statistics." As medical researchers, we must do better and we must strive to uphold the standards. And there's no shortcut to doing this other than getting to grip with statistics. Why is it important for physicians to understand statistics? What are the functions of statistics? The most important functions of statistics is to reduce data and summarize it so that we can make sense of the data. We do this by producing graphical means of visualizing data like tables, charts, etc., and by univariate analysis, which produce statistics like means, standard deviation, median, and the mode. By definition, univariate analysis makes use of only one variable. In this way, statistics help us to describe and understand the situation. This is the most basic form of statistics, and it is what we do with most descriptive studies. In addition, it is the foundation on which other statistics rest. Data in its raw forms are confusing and difficult to understand. Statistics is the tool that helps us to convert the data into information that we can more easily understand. For example, here is the data on 3 variables that were collected in the study. What can you make of this? What is the average age, for example? With statistics, we have turned the pile of the difficult to understand data into pieces of information that is actually useful. From the frequencies table, we can see that age has a mean of 8.09 years, a median of 7 years, and a standard deviation of 3.49 years. This tells us a lot about the properties of age in the community from which the data was obtained. Armed with this knowledge, stakeholders can act. That is the power of statistics. What is the second function of statistics? It is to carry out tests of significance. Supposing a study showed a reduction in back pain among manual workers from 5.5% to 3.1% after giving them a training on back pain prevention at work. How would we know whether this result was due to the intervention or simply due to chance variation? To find out whether results are due to chance or there is something else at work, such as the intervention given, researchers carry out tests of significance. Tests of significance are used for comparing observed data with hypotheses. The results of a significance test are expressed in terms of a probability that measures how well the data and the hypothesis agree. The third function of statistics is to help researchers select the appropriate designs for their experiments. Experiments have objectives. These objectives are achieved by using appropriate statistical methods. For example, in the study mentioned in the previous slide, one of the objectives in the study might have been to determine if the intervention was effective in reducing back pain. How might we achieve this objective? We might take a group of workers and give them a training on back pain prevention. We can then compare the incidence of back pain before and after the training. This is a before and after study design. On the other hand, we might decide to divide the study participants into 2 groups. Group 1 will be given the intervention in the form of training in back pain prevention. Group 2 will not be given the intervention. The incidence of back pain in both groups will be compared both before and after the intervention. This is an example of a control before and after study. With case control studies, you are more confident that the intervention is responsible for the effect you observed. Ultimately, tailoring the design of our studies to the statistics will make for efficient use of resources and more reliable outcomes. However, you need to do 2 things before you can use statistics effectively. You need the right software. You really do not need to calculate the statistics. The software will do it for you. But of course, you must understand the principles behind the statistics, and you must be able to interpret the results accurately. To use software in general, you must learn them. The same holds true for statistics software. Fortunately, There are many resources on the internet to help you do this. There are close to 100 statistics software on the internet. Of course, you can't learn them all. You only need to learn one or two of them and you are good to go. My favorite has always been SPSS. Why do I recommend SPSS? I recommend SPSS because it is the most popular software among researchers. The reason for its popularity is that it is not only powerful, but it is also easier to learn than many of its less popular rivals. Whatever software you choose to use, be sure to know how to use it well. More importantly, you must be able to interpret the output correctly. That is the bottom line. The second clue to the effective use of statistics is that your data must be collected in a scientific manner. One of the best methods of collecting survey data is by using mobile devices like tablets and smartphones. As you can see on the slide, there are many advantages to using these devices. They can collect data in many formats such as pictures, audio, and other digital modes that are not available to paper-based survey tools. In addition, they can record GPS and time data spontaneously. These two properties can help to guide against interview assistants filling questionnaires on their own. While these survey tools are not foolproof against research assistants who are determined to forge surveys, they guide against it better than paper-based alternatives. These are the three most popular apps for collecting data on mobile devices. They are all free and they are available on Android, iOS, and the web. What if you want to carry out a distant non-interviewer administered service similar to telephone service? The internet has you covered as well. There are many ways of distributing survey over the internet. In fact, the internet has become extremely popular as a way of collecting data during the COVID-19 pandemic, and this has come to stay. Google Forms, SurveyMonkey, and Microsoft Forms are some of the browser-based formats for collecting data. All data are not created or collected equally. Sometimes the data may need to be converted from one format to the other. The conversion may involve the distribution and structure of the data as well as cleaning of the data. In this lecture, we will only be dealing with the transformation of data that are not normally distributed. Why do we need to do data transformation? The answer is that most parametric methods of statistics have assumptions that must be met before you can run them and expect your results to be reliable. One of the most important assumptions of parametric methods is that the distribution of the data must be normal. The other name for normal distribution is Gaussian distribution. Data that are not normally distributed are referred to as non-Gaussian or non-normal or skewed data. This slide shows examples of normal and non-normal data. The graph at the top shows a normally distributed data. Note its symmetric bell shape. That is the hallmark of a normally distributed data. The two below are skewed distribution. Skewed data can be skewed to the left or to the right. The direction of the longer slope determines the terminology. Left skewed graphs have the longer slope to the left. They are also called negative skew because their coefficient of skewness is negative. Right skewed data, on the other hand, has positive coefficient of skewness and their slopes are to the right. The other quality of data that may need to be corrected by transformation is homoscedasticity. Simply put, homoscedasticity means having the same scatter. In this example, there is homoscedasticity because the two sets of data have similar distribution. This is statistics heaven because this is how you want the distribution of your data to be. The opposite of homoscedasticity is heteroscedasticity, which means different scatter. In the example shown, we can see that the two data sets are of different distribution. They appear incongruous. This slide shows how homo and heteroscedasticity appear on scatter graphs. A and C look similarly compact, so we can say they exhibit homoscedasticity. On the other hand, the scatter of A is different from the scatter of B. Same actually applies to B and C. The latter two show heteroscedasticity. Before you can transform data, you must first determine whether their distribution is normal. There are many ways of doing this. They can be categorized into graphical and non-graphical methods. With graphical methods, you can appraise the distribution of the data visually. The most commonly used graphical method is the histogram and normality plot. Statistical methods provide more accurate methods of appraising normality of data. The gold standard is the Kolmogorov-Smirnov statistics. In the following example, we have a data set containing two continuous variables, age and PCV. Our goal is to determine the normality of the two variables. The slide shows the output of running the normality plot in SPSS. It is obvious that age is right skewed, while PCV appears to be normally distributed because it is almost bell-shaped and symmetrical. The box plot from the explore procedure of SPSS reinforces our findings from the previous slide. Age has some extreme outlier, as we can see. In addition, the median is not in the middle of the box plots. The box plot itself is at the bottom of the graph. These are all attributes of skewed data in box plots. On the other hand, the PCV box plot is right in the middle of the graph. The median line is almost at the center of the box and there is no outlier. Certainly, the distribution of PCV is looking much more normal than age. The output of the explore procedures for PCV and age reinforces our previous findings. The closer the skewness and kurtosis are to 0, the more normal is the distribution. The scores of PCV are much closer to 0. We have 0.313 and minus 0.989 as the score of PCV, whereas the scores of age is 2.946 and 11.971. Similarly, when the 5% trimmed mean and the mean are close, the distribution of the variable is likely to be normal. In the example, the trimmed means of age and PCV is shown in blue, and we can immediately see that the trimmed mean of age are much further apart, 8.81 versus 16.56, than the mean and the trimmed mean of PCV, which is just 30.92 versus 30.65. The statistics shown on this slide points to the fact that PCV is more likely to be normally distributed, while age is likely to have a non-normal distribution. The gold standard of normality tests are the Kolmogorov-Smirnov test and the Shapiro-Wilk test. The former is used when the sample size is large, that is, when the sample size is greater than 30, while the latter is used for smaller samples. These tests are hypothesis tests of distribution. The null hypothesis is that the distribution of the data is not different from normal. Therefore, if the p-value is greater than 0.05, we will accept the null hypothesis and report the distribution as normal. On the other hand, if it is less than 0.05, we will reject the null hypothesis and report that the distribution is normal. In this example, the p-value can be found in the SIG column. We can see that the p-value of age is 0.000, We will therefore reject the null hypothesis for age and report that it is not normally distributed. On the other hand, the p-value of PCV is 0.260. This is greater than 0.05. We will therefore accept the null hypothesis and report that PCV is normally. Now that we know the distribution of the two variables, it is time to decide on what to do next. If the variable is normally distributed, go ahead and use parametric method to analyze the data. This is the case with PCV, and we will certainly use parametric method for the analysis of PCV. But what if, like age, the data is skewed? What will you need to do? There are three options of analyzing data that are not normally distributed. If the sample size of your data is at least 30, you can still use parametric tests for certain statistics. This is because the central limit theorem protects some tests from violations of assumptions of normality. However, you should know that for some statistical techniques, even the central limit theorem does not protect against violation of the assumptions of normality. So, when you are faced with the latter situation, you can transform the data to a normal distribution. What methods are available for data transformation? Three are commonly used in medical research. They include logarithmic, square root, and inverse transformations. In this example, we are going to transform age. In SPSS, the procedure to transform age is under the Transform Compute menu. We will instruct SPSS to do a logarithmic transformation of age to log age. The procedure will create a new variable, log age, in the data window of SPSS. In the following two slides, we will be comparing the distribution of the original variable age and the transformed variable log age. On this slide, the normality curve shows that log age is looking normal. The p-value of the Kolmogorov-Smirnov test for age is still significant at 0.002, but the transformed variable log age has a p-value of 0.304. This confirms that the variable has been transformed into a normally distributed data. In this lecture, we have covered the three objectives that we set out to cover. In the next lecture, we will be digging deeper into statistical methods for comparing groups, regressions, and correlations. I am Oluwade Akende, a professor of orthopedic and traumatology at the Ekiti State University, Ado-Ekiti, in Ekiti State, Nigeria. I have been teaching SPSS in healthcare research since 2004 in Nigeria and South Africa. I am also the author of the best-selling book on SPSS in Nigeria, Getting to Know SPSS, which also have supplementary chapters on Zotero and EndNote Reference Manager. It also has a supplementary chapter on online literature search. My website is at www.oluwadeya.com. Check it out for assorted information on my book. The website also contains more than 50 downloadable PDF copies of my lectures in anatomy and orthopedics. Finally, you'll come across assorted information about medical practice in Nigeria. Please subscribe to my YouTube channel, which I started on Saturday, July 10, 2021. This is the second item I have uploaded. In the next few weeks, I am going to add other uploads at the rate of 1 to 2 weeks. It promises to cover all my courses at both undergraduate and postgraduate levels. These courses include anatomy, orthopedics, and traumatology, SPSS, and general statistics. Stay along with me. The best is yet to come. Thank you for your time and attention. And as they say in my language, ẹ ṣeun.